Today, we're going to dive into a classic coding puzzle. How do you check if a Sudoku board is valid? But what's so cool about this isn't just the puzzle itself, it's the absolutely brilliant and surprisingly simple solution we're about to unpack. So let's just frame the problem. Put yourself in the programmer's shoes for a sec. You've got this 9x9 grid in front of you. How would you write code that only needs to look at each square one time to figure out if any rules are broken? That's the real challenge here. All right, so before we jump into any solutions, we have to be super clear on the rules of the game. What does a valid Sudoku board even mean? Okay, so here's the official definition. It's all about no repetitions. But that last part is really key. We can completely ignore any empty cells. This means we're not solving the puzzle. We're just checking if the numbers that are already there are playing by the rules. So it all boils down to these three simple checks. You got to check the rows, you got to check the columns, and you got to check those 9 little 3x3 boxes. If you can get through all that without finding any duplicates, you're golden. Sounds easy enough, right? Well, doing it efficiently is where the fun begins. So what's the first thing that pops into your head? If you have to check 9 of this and 9 of that, your gut instinct might be to just, track everything separately. You could totally create a separate list for each of the 9 rows to keep track of the numbers you've already seen. Encoding something called a HashSet is perfect for this. It's like having a bouncer at a club that only lets each number in once. So you'd make 1 for every row, 1 for every column, and 1 for every 3x3 box. It absolutely works, but you can probably feel it already. It's a lot. Yeah, 27. That's how many separate trackers you'd be juggling. 9 for the rows, 9 for the columns, and 9 for the boxes. It just feels a little clunky, a bit like overkill, and it's definitely not great for your program's memory. And the original source material really hits the nail on the head here. This method is space heavy, and whenever you hear that in programming, it's usually a giant signpost pointing towards a much smarter, more elegant solution. And oh boy, is there a smarter solution. So what if I told you we could throw out 26 of those trackers? What if we could do this whole thing with just 1? Yep, just 1. From 27 down to a single 1. Now that's not just a small improvement, that's a whole different level of thinking. This tells you right away that we're dealing with a seriously clever and efficient approach. So, how on earth is that possible? Well, the magic here lies in a brilliant data encoding trick. Instead of just tracking the number itself, we're going to track the number and its location, all bundled up into a clever little package. Okay, this is the heart of it all. Let's pull back the curtain and see exactly how these genius keys are built and why they let us validate the whole board so cleanly. So here's the game plan. We march through the board one cell at a time. If we hit a number, we instantly create 3 special little strings, our keys, 1 for its row, 1 for its column, and 1 for its box. Then we try to add them to our one big set. But before we do, we check, have we seen any of these exact keys before? If the answer is yes, bam, we found a duplicate. Game over, the board's invalid. If not, we just add our 3 keys to the set and move on. Now let's really break this down, because this is the secret sauce. Imagine we find a 5 in the very top left corner. That's row 0, column 0. We don't just add the number 5 to our set, no. We create 3 totally unique strings. 0R5 basically says, I've seen a 5 in row 0. 0C5 says, I've seen a 5 in column 0. And 0B5 says, I've seen a 5 in box 0. See what's happening? If we see another 5 later in that same row, it'll try to create the exact same 0R5 string, and our set will catch the duplicate instantly. Okay, I can hear you thinking, the row and column keys make perfect sense. But where in the world did that box index come from? How do we know which of the 9 boxes a cell belongs to? This little formula right here is the unsung hero of the whole algorithm. It looks a bit strange, but it uses a simple math trick called integer division, which basically just means it throws away any remainder or decimal part. By doing that, this one line of code can perfectly map any of the 81 cells on the board to a single box number from 0 to 8. It's super elegant and it just works every single time. So we have this beautiful logic. It works. But what makes it truly brilliant? Well, it all comes down to performance, how fast it runs, and how much memory it uses. In the world of coding, we have this thing called big O notation to measure how efficient an algorithm is. And this one? It's like it gets a perfect score. It's what we call O of 1, or constant time and constant space. But what does that actually mean? It's actually super simple. A Sudoku board is always 9 by 9, right? It's never going to be 100 by 100. So the computer knows at most it's going to have to look at 81 cells. The amount of work never ever changes. It's a fixed, predictable workload. And in algorithm terms, that's the fastest you can possibly. And the beauty is, this thing is bulletproof. You give it a totally empty board, no problem, it sails right through. A board with just a few numbers? Easy. A completely full and valid board? It checks everything and gives it a thumbs up. And the second, literally the second, it finds a conflict, it stops immediately. It covers all the bases perfectly. And that really brings us to the big idea here. This whole thing is a fantastic example of a core programming principle. Sometimes, the cleverest solution isn't a more complicated process, it's a smarter way of representing your data. By encoding the number and its position together, the problem just kind of melts away. So that's the question I want to leave you with. This encoding trick, this idea of creating a unique fingerprint for a piece of data based on its context, where else could you use that? What other messy problems could be solved with a simple, genius key? It's a really powerful tool to have in your mental toolbox.